Morning, everyone. We are starting our CMSA Colloquium. Today, we are pleased to have Gil Kalai as a speaker. Let me quickly introduce Gil. He is a professor at Hebrew University and at the Interdisciplinary Center in Israel. He got his PhD from Hebrew as well. And since then, he has spent time with many institutions, MIT, Cornell, Institute of Advanced Study, and other great places. He has won a number of awards, too many to enumerate. Among other things that Gil is currently busy with is maintaining a popular weblog where he discusses combinatorics and other things as well. And today, Gil will talk about what he thinks about quantum computing. Gil, the floor is yours.
Okay, thank you very much. It's really great to be in the colloquium. It would be nice to visit in person, to meet people in person, but this is how things are going. So I will talk about statistical, computational, and mathematical aspects of a NISQ computer, noisy intermediate scale quantum computers. And let me, oops, what happened? Okay, so two background questions. The first question is, are quantum computers possible? And this is a vastly important question. There are huge expectations inside the academic among academics and outside in the industry, very large investment, huge implications and consequences, and it is a clear-cut major scientific question. The second question that is a motivating question for this lecture is the Google demonstration of quantum supremacy valid? So here I refer to an experiment that was published about a year ago, and I'll mention it in a minute. But in any case, this is also a very important question. This event was compared to the Wright brothers' first flight, to Enrico Fermi nuclear chain reaction, and to the first vacuum tube digital computer in 1945, and also to the discovery of the Higgs boson. Let me try to do so that I can see the slide. This talk is mainly about statistical, mathematical, and computational questions, concepts, and ideas related to the study of these two questions. So I will mention several snapshots, mathematical snapshots. I don't always aim at the most significant bits, namely at this particular question, but some things that are derived from the study of these questions. And as you know, in mathematics, especially in my area of combinatorics, we not always are after the most significant bits. We see much beauty and interest also in the less significant bits. And we will have a mixture of the significant bits in this lecture. But I think the first thing I need to do is to describe what are noisy NISQ computers or noisy intermediate scale quantum computers. Let me just arrange this thing that it will be convenient. So, So NISQ computers are simply noisy quantum circuits with at most a few hundred of qubits. Now, this definition sounds a little arbitrary to many people who heard me speaking about it. And I would like to explain what is the conceptual difference between the scale of few hundred qubits and below and the larger scale. And the qualitative conceptual difference between the NISQ regime and larger scale regime is that in the NISQ regime, a single error in the computation process causes the whole circuit to fail. And this will be clearer later. Now about the Google experiment. Try to get announcements for the waiting room all the time. So let me see. So the Google experiment consists of a random quantum circuit. So it's a quantum circuit that the architecture of gates was, the gates were chosen at random, and their computer produced a sample of few million 0-1 vectors of length 53. And this sample is based on a certain ideal probability distribution P. And there are two crucial claims that were made. The first was that the fidelity, the statistical test for how close the sample is to the ideal distribution is sufficiently large, larger than 1/1000. And the second claim was that producing a sample with similar statistical property is beyond reach for current supercomputers. The support for both this claim was indirect. There is no way that neither claims, the first claim cannot be tested because computing the correct distribution probabilities will take too much on a classical computer, on any supercomputer, and this is part of the second claim. And the second claim is based on some theoretical evidence of various kinds. We still have this waiting room problem. Maybe the best thing is that you don't make me a co-host, but just allow me to share content, because this way the waiting room it still sabotage every step of the every time somebody enters the waiting room, it disturb my Sergio, you hear me? Okay, so this is the Google experiment. And let me briefly, before I move to the whole talk, let me briefly give you the answer to the two questions we asked. So the very brief answer is a no for both questions. And a slightly more nuanced, detailed answer is as follows. So are quantum computers possible? So I think that it is a serious possibility that quantum computers are not possible, and this is what I expect and study. Is the Google demonstration of quantum supremacy valid? The Google claims are not convincing, and there are serious concerns regarding their experiment. So here is a cartoon from 2017 that more or less explain my position. What about the efforts of Google, IBM, Microsoft, Intel, Alibaba, and so on and so forth? Many groups, both in industry and in academic, in universities or other academic institutions, to reach very stable qubits and demonstrate quantum supremacy. And I think that they will all going to fail. And another footnote is that you should not expect false positive for high quality encoded qubits. Quantum supremacy is more vague question, and there I didn't know if to expect a false positive, and I think we have witnessed now a false positive. Okay. Okay, so my lecture today consists of 12 snapshots. For more, I can refer you to the following papers. The first is the paper with Yosi, Rinott, and Shoham, statistical aspects of the quantum supremacy demonstration, and the others are papers by myself. Or the recent one is also referred to the Google experiment, and the earlier one is from the proceeding of the 2018 International Congress of Mathematicians, and it is in a wider scope about connection between mathematics, computation, and games, but one chapter is about quantum. So here is our first snapshot, and this is a very nice idea, and I want now to describe to you the Porter-Thomas distribution. And for that, let me say that the ideal state of a quantum computer is based on is a device which has n computing components called qubits, and the ideal state of a quantum computer with n qubits is represented by a unit vector u, which is u1 up to um, in an m-dimensional complex vector space where m is 2 to the n, 2 to the number of qubits, and the coordinates of u are referred to as amplitudes. Now, when you measure the state, you get a single sample from a discrete probability distribution with probabilities W1 up to Wm, where W1 is the absolute value of U1 square. I'm sorry, there is a typo here. W2 is the absolute value of U2 square, and so on and so forth. Wm is the absolute value of Um square. So when you have a unit vector, you get a discrete probability distribution. If you start with a random unit vector, then these probabilities themselves are distributed like exponential random variables. And actually, a slightly more precise description is Dirichlet variables. But let me explain. But when n is large, it's behaved like exponential random variables. Let me explain how you get these exponential random variables. Each real coordinate of each complex coordinate is distributed like a Gaussian. It's very close to a Gaussian distribution, because if we take a unit vector in a real vector space, then the coordinates are very close to being a Gaussian. And then when we take the sum of the sum of squares of two Gaussian variables, we get exponential variables. Now, the resulting probability distribution on this M discrete space of size M is called the Porter-Thomas distribution. And this Porter-Thomas distribution appeared in quantum physics in fairly similar connection. And let me go on. So here we see the Porter-Thomas probabilities, and here they are already adjusted to the fidelity level. And we see that this is the case of 12 qubits, they nicely agree with the Google sample taken from the quantum computers. Let me draw to you the basic picture of the juggling of the various probability distribution that we see here. We start with a real distribution, which is in this case exponential distribution, and then a real positive distribution. And then we take a sample of length m from this distribution. This sample of length m normalized so that the sum of all these values will be 1, define a new probability distribution. This is a discrete probability distribution based on the sample. So we have now a new probability distribution on a space, a discrete space of size m. And then the next step, which is what the Google experiment do, is take a sample of length n from this probability distribution. So had we have a perfect quantum computer and we ran on it a random circuit, we will see something fairly similar to that. But there is a few twists in this basic picture that I want to draw your attention to. The first twist is that we don't start from a single real distribution, but rather a mixture of two or more distributions. One of those distributions represents the ideal quantum computer, but the others represent the effect of noise. The second caveat is that the sample is not truly a random sample. If it was a truly random sample, there was no difficulty to simulate it. But rather, it's a pseudo-random sample that the pseudo-randomness is described via the quantum circuit. And the whole point is that an ordinary computer cannot imitate this pseudo-random sample. And the other caveat is that, remark is that the M entries in this large picture in the finite probability distribution, they correspond to 0, 1 vectors of length n. So the outcome of the experiment are a bunch of 0, 1 vectors of length. Okay, so this was the first snapshot. I should say that the general description that I draw you here fits into something studied by statisticians under the name of Kingman distribution. And they had a motivation which didn't come from quantum physics. And it's a very nice statistical setting. And now we are ready for our second snapshot, second idea. And this is the notion of size bias distribution. So suppose you want to estimate the distribution of the number of people in apartments. So what is the probability, or what is the probability that in a random apartment you will have k people living, where k is a number 0, 1, 2, and so on. And then suppose you make the following experiment. You sample random people on the street and ask each one of them how many people share, and ask each one how many people share their apartment with them. You get a new distribution, and the answer, the distribution E of answer will not be identical to your original distribution. And a quick way to see it is to note that you will not meet anybody in the street from empty apartments. So even if 20% of the apartments are empty, your experiment will not show that. And more generally, the larger the number of people in the apartment, you will get a bias for larger apartments. And the new distribution, E, is, okay, so I'm sorry, I mixed here some Latin letter, but the new distribution is called the size bias distribution corresponding to the original distribution. So if the original distribution D is exponential, namely has density e to the minus x for positive x, then the size bias distribution will be gamma to 1, namely it has density x times e to the minus. And we face a similar situation in the Google experiment. So here, just to use our previous picture, we start from a real distribution, we move to a discrete distribution, and then we just add one more component. There is the size bias distribution, which corresponds to our real distribution. So if we start from an exponential distribution, the size bias distribution is a gamma distribution. And here again, taken from the Google data, we see a remarkable agreement for the size bias probabilities. They are also adjusted to the fidelity level between the theoretical gamma 2-1 distribution and the empirical data. Okay. Okay. Now we come to the the third ingredient, and it is modeling the noise. And the problem in the NISQ regime, a single error causes the circuit to fail. I should say, there are some caveats about this sentence. What do we mean by a single error? Because when we run a gate, the question if this gate act correctly or incorrectly is only manifested much later at the time of the measurement. But this is still, after all these caveats, this is a good description of the situation. And the idea in modeling the noise of the Google basic noise model is that the noisy distribution is P times the ideal distribution. This is the probabilities produced by a quantum computer, an ideal quantum computer without any noise. And then the effect of every noise is to replace this distribution with a uniform distribution on all the 0, 1 bit string of length n. And this is the model. And in other words, the model is a mixture between the noiseless distribution and the uniform distribution. And as we shall see, to identify this number phi, this fidelity is very crucial in this study. Okay, so one observation we made is or interesting observation is that the experimental data does not fit. We in our paper we only studied the very early experiments of 12 qubits, and what we see here, and this is you see it in this diagram, that the experimental data does not fit the noise model, and so far we don't have a good description of the noisy distribution. So we have a somewhat improved readout model that I will mention in a minute, but it only gives a slight improvement. So I should say it's not clear what is the noisy model, and in a sense, and I will explain it a bit later, it's not clear if there is any stationary model which describes the data. Okay, so now I come to the next snapshot, and this is how to estimate the fidelity. And this is a very nice piece of statistics. Overall, the Google people do a good statistical work. There are few improvements that are possible. And here is the basic estimate. So you start with the sample. So you let your quantum computer produce n, capital N bit strings, and for each of this bit string, you use a classical computer to compute what is the probability you would expect if there was no noise at all. And then you add all these probabilities, take the average, divide by the number of by n, and subtract 1. And this is the estimator U. And overall, it is a good estimate. It's a fairly good estimator. It does not depend on the specific noise model, but only on very basic properties shared also with the other models. It turns out, okay, let me, before I discuss some issues, I should explain the crucial statistical philosophy. Once we use numerical simulation to compute the probabilities, we can recover the empirical size bias distribution and estimate the fidelity from relatively small samples. So remember that if we have a 53 qubits, then we are talking about a sample space of size 2 to the power 53. And yet our samples are fairly small, they are few millions. And the reason that we can make it work is that we can, on the side, we can compute the ideal probabilities we expect for every bit string. And using these ideal probabilities, we can see if there are some biases. Essentially, we can estimate that we cannot recover the discrete probability distribution because this is a probability distribution on a space of 2 to the 53 of size 2 to the 53, but we can still cover the empirical size bias distribution. And from the empirical size bias distribution, we can recover the fidelity phi. So this is the philosophy. Okay, here is again, I added it to my basic picture. So we have here a mixture between exponential distribution and the noise, which is represented in the model case by a constant distribution. And then we move from it to a discrete probability space of length m. And from this space, we take a fairly small sample of length n, but the idea is that if we can compute the probabilities, we can get a very good picture of the empirical size bias distribution and of the fidelity phi. Now, what we notice, so we notice that there is a conceptual difference here. I don't know if you follow all these diagrams, but you see we start from one distribution, real distribution, then we move to a sample based on this distribution, which is a realization of this distribution. And this realization enables us to create a new distribution. And then we sample according to this new distribution. And when we talk about estimator, we have to distinguish if we are estimating over the entire family of all the random distribution, all the Porter-Thomas distribution, or if we estimate based on the specific realization. And it turns out that this makes a difference. The Google sample U is no longer unbiased if you fix the realization, which is arguably more relevant to the experiment. And what we found out is that well, we compared several estimators. Some of them are also mentioned in the Google paper. And you see here the picture in terms of the variance, how it depends to various parameters. And consistently, the maximum likelihood estimator, the famous MLE estimator that was much studied by Fisher, gives the optimal result here. And even U itself can be improved when you take the realization into account to another estimate, which we call V. But when the number of bits is larger and the fidelity is small, then the behavior of all these estimators is quite similar. Okay, so now I want to talk about another aspect of the Google experiment, and this is a more realistic view of the noisy distribution. So I think a more realistic noise model is that the noisy distribution can be seen as a mixture between the ideal distribution and some fluctuation of the uniform distribution. It's fairly unrealistic to think that the effect of the noise is a mixture between the ideal distribution and the uniform distribution. You can see that if you take a mixture between ideal distribution and uniform distribution, essentially you don't lose any information. And that there are other reasons why this is not so realistic. And we try to study this fluctuation. The fluctuation of the uniform distribution give you a sort of a secondary signal. So one way to think about the Google experiment is that this exponential distribution gives you a signal of mountains and valleys that manifest this pseudo-random quantum computing, and that you try to verify that this signal exists in the sample data. And what we point out that there is a secondary signal which also depends on the circuit, and this signal depends on the types of errors we can study. One type of error, which is very simple, is that when you measure a qubit and the results should be 0, you get instead 1, or vice versa. Those are called readout errors. And one part of our study was to study what is the effect of this readout error. And it turns out that this gives you a secondary signal which allow you to give an alternative estimation of the fidelity. So this is one part of our work. And you can see here you can see when we eliminate the primary signal, we talk only about the readout error minus the primary signal, and we compare the data with the model. We see a cloud that there is you almost see nothing here, but still there is some positive correlation which depend on the fidelity and allow you an alternative estimation of the fidelity based on this finer structure of the signal. Okay, so and now I want to talk about another aspect which I think it's very interesting. It is related to some earlier studies, and this is the Fourier connection, or what happened where you expand the probability distribution, which is a function. You can think about it as a real function on 0-1 strings of length n. You expand it in terms of what's called the Fourier-Walsh distribution. So I should say that expanding function on 0-1 to the n based on the Fourier-Walsh distribution is a fairly important theme in combinatorics and theoretical computer science, and in particular in the study of noise. And of course, the basic property is that every function p can be written as the sum over the sum p hat of s ws of x, where p hat of s is the Fourier coefficient and ws of x are the Fourier-Walsh functions. And here the sum is over all subsets of 1 up to n. And now when we look at the noise with the eyes of the Fourier distribution, we see that the Google noise model is very simple. The noise, the Fourier coefficient which correspond to the empty set remains the same, and the Fourier coefficient which correspond to every other set is multiplied by this fidelity phi. So this is the Google noise model. And then a more realistic model, which we can call the heat kernel noise, cause the Fourier coefficient to diminish in a way which is exponential in the size of the index set. So the Fourier coefficient of the empty set will be the same, will remain unchanged, and this actually because it's the probability distribution. But the Fourier coefficient of the higher Fourier coefficient will be multiplied by t to the size of s for every s which is not empty, and t is a certain parameter, and you can compute the fidelity from t and t from the fidelity. So the idea that this is okay, let me start with the second paragraph here. The idea that Fourier description is useful to study a probability distribution for NISQ systems, noisy intermediate scale quantum system, started in a work which I had in 2014 with Guy Kindler. And this work was not about noisy quantum circuits, but about another model which is called boson sampling. And the connection between Fourier-Walsh evaluation and certain aspect of noise already go back to some work I did with Itai Benjamini and Oded Schramm about noise stability and noise sensitivity. And also I should mention that there is a very interesting related statistical notion, which is called the ANOVA decomposition. And it turns out that both me and Yosi Rinott, we both work on this project, we studied similar thing. I studied the Fourier-Walsh decomposition in the study of Boolean function and the study of the effect of noise on Boolean function, the effect of mistakes in counting votes in election. And Yosi Rinott studied it in the connection with the ANOVA decomposition and the so-called Fron inequality around the similar times in the 80s. Now we are working on developing statistical tools to understand the Fourier behavior of distributions based on sparse samples. So one of the lessons we get from the statistical study in the Gould experiment that you can do quite a bit based on when you try to study statistically the output of quantum computers, you can do quite a bit using sparse small samples that are too small to get the entire empirical distribution. And we try to extend this idea to the study of Fourier, of the Fourier behavior. And now I want this is the seventh item. Now I want to explain to you briefly the behavior of noisy intermediate quantum systems where we use this Fourier lens. And the first aspect is what we can call the computational simplicity. And here, and this is something which goes back to my earlier work. It is not related to the Google experiment. When we have a constant level of noise, and this is a reasonable, reasonable assumption when we model quantum computing. When we have a constant level of noise, then the computational power of NISQ systems is very limited. And I don't want to get much into computational complexity, but here is a picture showing you how limited it is. On the left, we see a brown circle called P. This is what computers can do. This is the computational class P, a polynomial time. Here I allow randomness, although so maybe you use different letters, but so for me, P is polynomial time computation, even if with randomness. As you know, P is strictly contained, as far as we believe, in a much larger class called NP. This is a non-deterministic polynomial time, and whether NP is equal to P is one of the important questions in mathematics. And the NP is contained in much larger and larger hierarchy of the computational class, which the union of them is what's called the polynomial hierarchy. There are even things which go beyond the polynomial hierarchy, but let me not mention them here. And you can also see the ellipse Q, and Q represent what quantum computers can do. So quantum computers can do well above P. For all we know and believe, quantum computer cannot solve NP complete problem. But on the other hand, quantum computer can solve problems which are even beyond the entire polynomial hierarchy. So here is the picture on the left. Now, everything is out of scale. So P8 is much, much larger than P and so on. Now, inside the P, you have a very tiny computational class, which is called bounded depth computation. And bounded depth computation is very limited. For example, you cannot compute the parity of n bits using bounded depth computation. And inside bounded depth computation, there is a small, even more restricted class. And here I refer to class for sampling problems, or I juggle between different types of computational problems. And this is called the LDP. This is a class that Guy Kidler and I identified. And these are probability distribution that can be approximated by low degree polynomials. And this probability distribution can be sampled using bounded depth computation. And noisy, the computational power of noisy intermediate scale quantum circuits is well inside this very, very small computational shells. So this is one conclusion from this view of noisy intermediate scale quantum systems, modeling the noise using this heat kernel description, is that the computational power of NISQ system is very, very simple. There is another conclusion which is in a different direction. It says, even if the noise level is subconstant, for wide range of subconstant noise levels, the outcomes will have vanishing correlation with the ideal distribution. This is called noise sensitivity. And moreover, we can expect that the outcome will represent chaotic probability distribution. So there will not be a stationary distribution, and even stronger, you will see large chaotic effect for a NISQ system. So here is so the description of the world, which is true for NISQ systems and probably extend for larger scale simple systems. For large amount of noise or large entropy, you can have classical information and all the computation we see in nature. When the amount of noise is even smaller, all you can see is low degree polynomials. And for smaller amount of noise, what you can see is chaos. And then for extremely low, beyond reach amount of noise, then suddenly you can see what's quantum or superior quantum computing, but this is beyond reach. So with the Google data, we also try to study so far for 12 qubits, is the noisy distribution stationary? And we realized that if you take, so they provide, Google provided the 500,000 samples for a certain number of qubits, 12, 14, and so on. We mainly work for various reasons only with 12 and 14 qubits. And we saw that not only that the distribution is fairly remote from the noisy model, but the first half of the distribution is far from the second half of the distribution. This is not manifested at all by the fidelity. So if you look at the L1 or L2, this distance between the first quarter samples and the second quarter million samples, you see that they are fairly far apart compared to a random split of the 500,000 samples to 2 random bits. So we do witness already for n equal 12 this non-stationary behavior of distribution. Some aspect of the non-stationary behavior, which is not chaotic, we can identify. For example, some bits tend to be closer to 0 in the beginning and then get linearly toward 1 and vice versa. We still expect that there is also a chaotic ingredient, and we develop tool to try to statistically study these issues. Okay, so let me move now to the 9th snapshot. And this is an interesting idea in regarding statistical studies. And this is the idea that when the experimental results fit the expectations of the researcher in a statistically unreasonable way, this is a sign of a serious methodological mistake. For example, a biased data selection or some other mistake. So this is a sort of a famous and interesting phenomenon. And the famous cases are the Mendel landmark experiment in genetics. In this case, of course, the science was correct and spectacular, but there are good reasons to think that the actual outcomes of the experiment were too good to be true. Whether it was Mendel's fault or his Gardner, it's still in dispute by historians. Another famous example, or infamous example, is the Cyril Bert experiment on IQ for twins. There also the theory matched the data in a way which is too good to be true. And in the Google case, the experimental outcome fits the a priori fidelity prediction in unreasonably well. So it is too good to be true in the Google case. So recall that in the NISQ regime, a single error causes the circuit to fail. And this is the basis of a formula, Formula 77 in a Google paper, which gives an a priori estimate on the fidelity. For each component, whether it's a qubit in Q or a one qubit gate or a 2 qubit gate, you compute the probability of an error, and then you take just the product of all these numbers, and this gives you an a priori prediction for the fidelity. And this prediction is very crucial. This prediction is not crucial for building quantum computers, but it is crucial for the specific argument that Google used, because they use some sort of extrapolation, and they claim that this a priori formula fits the experimental data up to 10 to 20%. And when you analyze this, you realize that this requires unrealistic statistical independence. And it would be interesting to test the statistical independence of readout errors based on some raw data used in the Google study that we right now don't have. And in any case, this is a serious reason for concern. Let me just mention very briefly that in a previous talk I gave about it, a famous physicist, Amanda Weltham, commented, I would like to ask you about your claim that we should think twice when the experiment matches too well the theory. Yes, there are examples where this is a bad sign, but there are also examples where it is not. Just look at the C and B spectrum theory, best data curve, the first peak is basically spot on, and I completely agree. So usually such an observation, but I should mention, I didn't, let me go back in a minute, but this is usually just the beginning of the story. And also here, I suppose it will take a couple of years to understand what's happened in the Google experiment as in similar cases. I should say, I didn't expect, first of all, this is a picture from my blog. And here you can see, so about 20 years ago, I was involved in another study where we studied certain statistical claim based, and one of the arguments in refuting it was that some aspect of it were too good to be true. And then later, Maya Bar-Hillel, who was one of the co-authors of this 20-year-old study, had led some project about the possibility of systematically using statistics to find mistakes in statistical experiments. And she had a catchy name for it, How to Catch Lies with Statistics, in certain conference for Esther Samuel Cohen. And this is, by the way, a picture from my blog. I gave a talk about it. We have this picture, and in the audience was Dror Bar Natan. So we had sort of a virtual Zoom reunion of some of the researchers from this old place. Okay, and here is let me just go quick on that. Is a statistical mystery that when we compare the data to the model, we see the gap is asymmetric, and this is something which we are quite curious about. Okay, so now I want in the last few minutes of the talk, again, in a very quick way, to give you my arguments very briefly against the quantum computer. And part of it you've already seen. Noisy intermediate scale quantum systems, NISQ systems, represent a low-level computational ability that will not allow using them for demonstrating quantum supremacy or for building quantum error correcting codes. So the NISQ, in the NISQ regime, you don't have sufficient computation power to demonstrate quantum supremacy. You don't have sufficient computational power to demonstrate to build quantum error correcting codes which are harder than demonstrating quantum supremacy, and therefore you will not be able to do anything even in the higher regimes. And a nice way to describe this idea is that we can talk about three basic parameters of noisy quantum systems. Alpha is the rate of noise required by large quantum computers. Beta is the rate of noise required for good quality quantum error correcting codes. And let's be specific and talk about distance 5 surface code. Gamma is the rate of noise required to demonstrate quantum supremacy. And delta is the lowest realistic rate of noise. And my argument is based on the strict inequalities that alpha is smaller than beta. Well, this is, of course, everybody realizes that. And the rate of noise required for quantum error correction is smaller than what is required for quantum supremacy. This I didn't mention here, but this is also not in dispute. And the crucial computational complexity argument is that the rate of noise required for quantum supremacy is below what can be realistically achieved. And this is based on the computational complexity argument that I mentioned. And this is what in dispute because many researchers are completely sure that pushing delta to 0 is simply an engineering problem. So they think that in principle, delta can be pushed to 0. And then we say that in principle, delta cannot be pushed down below a gamma. And this is similar computational complexity argument to the one that you cannot compute, say, complicated Ramsey number. So here I want to mention, this is the last item, and this is the notion of naturalness. And this is a very interesting thing about how to bridge computational complexity and computational reality. So let me describe you this idea. It's fairly isolated from all the others. Our main tool for the study of complexity of algorithms are asymptotic. For example, we make distinction between exponential running time and polynomial running time. When trying to gain insight into practical question, we need to make an assumption of naturalness. Namely, what is the constant involved in the asymptotic descriptions are mild. Without naturalness, we cannot, we hardly ever can turn computational complexity insight into real life situation. And with naturalness, we do gain much insight. If an algorithmic task can be solved asymptotically in polynomial number of steps, then usually this suggests that the task is practically feasible. And if a class of algorithms or computational device represent polynomial time computation, then we cannot expect that the class of algorithm will practically solve intractable. And this is a heuristic but a powerful notion. And I should say, both the rationale for the argument in the Google paper that they demonstrate quantum supremacy and my rationale that against quantum computers, they are heavily based on naturalness. So perhaps a last item which is, I think, very, very interesting, is consequences for physics, but we will not talk about it today. We talk about statistics, a little bit about mathematics, a little computation. Let's leave it for some other talk, but you can look at it in this paper that is written here. And another thing that we will be very happy, we think that our statistical study is relevant to other NISQ systems. We'll be very happy to get samples from IBM quantum computers with simulations from other groups. And let me move to the conclusion of this talk, which is about time. The question, I think, somebody want to be admitted just now, which is a fairly good timing. The question if quantum computers are possible is a clear-cut scientific question. A negative answer is a serious possibility, and it may shed light on important questions in quantum physics. Far from being among the notable discoveries of the century, the Google supremacy demonstration may offer some understanding of the limitation and weaknesses of technology and of scientists. I should mention that we should, let me make another remark, that proposal for small improvement based on quantum effects should seriously be considered. Although the hopes are for exponential speed up, there are very interesting ideas, and I heard a very lovely talk by the late Israeli physicist Yaron Silverberg, how to use quantum effects to improve electronic microscope or MRI or other things, and this is a very important topic. And let me mention that there is a silver lining that both in the case that quantum computers are possible and in the case that we'll understand why quantum computers are not possible, the silver lining is the progress that we can expect, a progress in our ability to simulate noisy quantum system both ways. So, so thank you very much. Here is the pictures of institute that I belong to and the grant agency that I'm very thankful for their support and some other things. And thank you again for inviting me. Thank you.
Thank you very much for the talk, Gil. Do we have any questions from the audience? If you have a question, please just unmute yourself and go ahead.
Hi, can I ask a question?
Sure.
Hello. Yeah, so like, do you have exact numbers for alpha, beta, gamma, and delta? Like, how do you exactly know that? I mean, like error correction, it makes sense. Like, but I'm thinking like, you know, like the other two numbers that you put there, like, do you have a mathematical justification for that and a quantitative number like?
No, so the argument just give you these strict inequalities. And I should say that these constants are not entirely universal constants of nature because they depend on the architecture of the quantum computer or the quantum system, but they depend on the architecture in a mild way. So if we are talking, for example, about a single qubit, we can consider an experiment that we start with a single qubit and we make a 10,000 or random gates, one gate, then I would expect that after that, the qubit will be completely destroyed. And this 10,000 I would expect this to be true. But my argument, my theory don't give you a numerical value. They only give you, there is asymptotic reasoning that give you the connection between these two constants.
So do you have like, you know, some kind of theorem, the structure where, you know, like so do you have like some kind of, like, I mean, even if let's say you do not have a number, but do you have some theorem proof kind of a structure where you rigorously prove that these numbers, you know, should have like a particular inequality structure?
So as I say, I think they are good. So there are good computation complexity reason to believe that alpha is smaller than that the constant that we can achieve is larger than the constant which suffice for quantum supremacy.
I mean, the reason, you know, like, I mean, the last one of the constant which you say that the noise we can achieve in nature, I mean, to me, that sounds a bit vague. Like, I mean, how do you characterize that, not like that constant, like mathematically? Like, I mean, I'm curious to know that.
So let me share screen again, and we'll go to this constant. There are still two people that entered the waiting room. What happened? Okay. Do you see my, okay, my slides?
We do not see, like, I mean, at least I cannot see.
You cannot see the slides. Wait.
Yeah, I mean, I think maybe you need to share.
Okay. Let me try again to share screen. Okay, do you see it now?
Yeah.
Okay, so alpha is the rate of noise required for universal quantum computing. Delta is the lowest realistic rate of noise, and gamma is the rate of noise required to demonstrate computational supremacy. So my argument is that gamma is smaller than delta. So do you ask, do I know precisely what, or do I have some mathematical description what these numbers are?
No, so I mean, like this, the lowest realistic rate of noise, like, I mean, I'm asking, like, how do you quantify that? Because this is something, you know, like, it's something like, I mean, I will at least think it will be difficult to define, like, what is realistic rate of noise, like which physical principle you are using to find out the upper bound, like the lower bound on the noise that can be physically achieved. Like, I mean,
okay. So let me, okay, how we find it is that, let me say how to define it. So I think one way to define it is you take any system, any physical system that realize a qubit or 2 qubits, and let it run by a certain amount of times, apply a random gate n times, and look at the minimal number, look at the value of n until the entropy of the system is larger than, say, 0.2. So this is a parameter that gives you some definition of the quality of the cube. And the assertion that gamma, the assertion actually that beta is bounded away from 0 means that no matter in any system you will implement, then this number will be relatively small and probably not much larger than what can be achieved today. Maybe
Professor Kalai, like, still I cannot like see any physical argument. I mean, because the last constant you are talking about is, you're saying realistic rate of noise. So I mean, I need some, you know, like physical argument, like some argument from physics, like which should tell me some kind of no-go theorem, which tells me that I cannot go beyond that. Like which
so
physical argument you have?
I think the realistic, the new argument from physics is that we are talking here about physical systems, and we estimate, we have an unknown parameter, which is the rate of noise. And the reason I tell you that the rate of noise is large is not based on a specific physical mechanism that I identify, which can be very different for different systems, but it's based on the computation ability of this device. So you give me a device, and I tell you the reason that you cannot have the noise below the fidelity below the gate fidelity smaller or larger than 0.99995 is that if you could make it, you will demonstrate a primitive computational machine that compute a intractable computation. So this is the type of argument. Now, of course, you are hoping or expecting something different, and you are not the only one. This is what most physicists and many computer scientists, many people think there will be some other reason. You will be able to tell me some specific physical reason why the noise will be large. And I give you an indirect. Yes.
No, I mean, like I appreciate, this line of thinking and all. It's just that, still like I cannot see things very precisely mentioned. Like I'm just trying to learn, see whether like if, for example, like in the case of Bell scenario, if somebody says me that you cannot move fast, like, you cannot have communication faster than the speed of light, that's something, very precise, like well put, and people will buy it. Here you are talking about different physical systems, and you are talking
usually when we draw conclusions from computational complexity argument, so if I can tell you we will never be able to compute something, there is a famous case, there is a famous problem in combinatorics of computing the Ramsey number, and the eldest famously said that if some alien would come to Earth and tell you, compute the Ramsey number 5, or we will destroy you, then you should put together all your mathematicians and computer scientists and compute this number. But if they ask for the number, the Ramsey number 6, the 6th Ramsey number, then there is no hope to do it, but you should try to fight this alien. So this is the typical way computational insights played out. They don't give you. So, for example, there is a paper recently which show a machine for factoring integers using classical device. So this was a paper in Nature, and of course the reaction of everybody in the field is that this is extremely unlikely because factoring we don't expect it to be feasible for a quantum computer. So this is also a reasoning based on computational complexity, although it doesn't give you precisely what is the physical reason that this suggestion will fail. Usually the suggestion is sufficiently undefined or vague that you cannot, there is an underlying computational principle which tell you that this device, this proposed device is going to fail. And by the same token, a noisy intermediate scale quantum computer are going to fail to produce intractable computation.
Professor Kalai, I will just add, the last line, because last argument before, like, I think I'm taking time of others. So basically, like, I mean, I appreciate these complexity theoretic arguments and all, but, like, I mean, in the process, you are also defining this LDP class, and, you are talking about this class of low degree polynomials, which, within P and and so on. But often, like the separations between the complexity classes are not shown. And there is a lot of belief that, people have tried and so for example, the diagram which you made for Q going beyond polynomial hierarchy, we all believe that, something like that could happen. But I mean, it's all belief. I mean, there is no physical principle telling us that, I mean, it's just that smart people have tried and failed, and different beliefs have different amount of, some belief is more sacrosanct than another. But in the community, in the community of computer scientists, do people all believe that, the reasoning that we have with respect to this complexity theory, is it like something universal? Like, does everybody believe, or there is a lot of disagreement there?
Okay, this is sort of a separate question. So I should say that I think there is, if you ask about, for example, that NP is bigger than P, this is a large this is largely believed, and but I should say that as far as my and Guy Kindler very tiny complexity class LDP, this is a case you don't have to believe, because this is such a small complexity class, you can actually mathematically prove that it's very limited and it cannot make involved computation.
But
So,
Michael's paper basically.
But I should say that let me just add that the idea that you can use computational complexity insights for telling you about the physical world, I think this is a valuable idea. It's not my idea. Other people think so, and I think this idea may not work so well for P and NP, which are very high-level computational class. It's not clear they are relevant to the real world. But for this low-level complexity class, I think it's a useful idea that the computational complexity insight tell you about the behavior of noisy physical systems.
Okay, thank you very much for the discussion. I'm afraid we do not have time for more questions. So if you have any more questions, please ask Professor Kalai directly via email. Thank you very much.
Okay, great. Thank you very much.
Thank you. Bye-bye.
Good talk. Thank you.
Thanks, Gil.
Talk.
Yep.
Thank you.